Thank you. And now we want to pass the floor to our British colleague, and the British Antarctic Survey of the UK, Marshall Gareth, will make a presentation on recent Arctic climate change.
Okay, thank you, Sergey. I'm going to attempt to share my screen now. Okay, I hope everybody can see my screen now. So
Yes,
my presentation then is recent Arctic climate change, and by that I mean change over the last 50 years or so. And then hopefully, if I have time, I want to end with a few slides talking about how we think the Arctic climate may change into the remainder of the 21st century. So as Alexander mentioned, Arctic climate change has been very rapid, so it presents many challenges to us. So I've illustrated some of these here just for a little bit of context. So on the left-hand side, we have what we call drunken forests, which are a consequence of the melting of permafrost. So the roots of the trees become unstable and they sort of topple over and grow at these rather ridiculous angles. The second photograph shows the results of what we call a rain on snow event. As temperatures rise in the Arctic, we have a higher proportion of precipitation that falls as rain. And so when this rain falls, it can percolate into a snowpack where it will refreeze and form a dense layer of ice within the snowpack. And this means that grazing animals like reindeer are unable to reach their food underneath the snowpack, and therefore we get these sort of mass extinction events that you can see here. And then the third photograph shows coastal erosion. I think this is in Alaska. Previously, the north coast of the Arctic was covered, or the ocean next to it was covered either in fast ice or sea ice, which formerly protected the coast from wind and tidal erosion. And as this melted, this was no longer the case, and we've seen some very rapid examples of coastal erosion. So many challenges, but of course, just to be fair, we should also mention the opportunities, which I'm sure you're all well aware of. In particular, as Arctic sea ice continues to decline, the northern sea route will become more frequently open, and that will give huge economic opportunities, particularly to Russia, because it's obviously so much more economical to transport goods from Northern Europe by this route than going through the Suez Canal. So that's a little bit of context. So just to quickly go through the outline of my talk. Some of the climate parameters I'll be talking about then are temperature, precipitation, sea ice, snow cover, atmospheric circulation or teleconnection patterns. And then, as I said, hopefully I'll have time to mention something about the future of Arctic climate from model projections. And here I should also mention some of the things I'm not going to talk about because of time constraints. So I'm not going to talk about the non-frozen part of the ocean. So I won't be mentioning changes in salinity or ocean currents. And there are also some aspects of atmospheric climate as well. So I haven't mentioned clouds, which I know Alexander mentioned briefly, and also troposphere, stratosphere linkages, which are actually very important in getting this signal of Arctic change down to the mid-latitudes, where most of the population live. There's a lot of work on that going on at the moment in the literature, but unfortunately I don't really have time to get into the details of that today. Okay, so next slide. So, or Arctic climate change in context. So this figure on the left is temperature trends over the last 50 years from 1969 to 28 from reanalysis data sets, which we often use in the high latitudes because of the lack of conventional observations. So what you can see here is that there is clearly very little cooling anywhere on the planet. Most of it is confined to the oceans. In terms of the warming, you can see that we see greatest warming at both high latitudes, but in particular in the Arctic, and you can see the highest warming rates are in the North Atlantic, particularly around Svalbard and then into the Barents Sea. And clearly this represents a change from when we used to have sea ice to now that we don't. So these particularly high increases in temperature are caused by a decline in sea ice. If we bin that figure by latitude, we get this figure on the right-hand side here. And you can see that the largest warming has taken place at about 75 degrees north. We're looking at values of about 0.7 degrees centigrade per decade. So that's about 3.5 degrees centigrade at this particular latitude over the last 50 years. So this greatest warming in the Arctic is often called Arctic amplification. And I've got another graph showing that here. This case, it is based on station observations. So we're comparing the global change in temperature anomalies in the red line versus the Arctic anomalies in the blue line. And clearly over the last 50 years from about 1970, you can see that the rate of warming in the Arctic is greater than globally, and the amount of amplification is usually thought to be between 2 and 3 times the global average. So why is Arctic amplification taking place? So this plot at the bottom of this slide attempts to sort of show that as a sort of a cartoon diagram. And it shows the important feedback mechanisms and processes that are involved. The key one is this one shown in red here, which is the direct surface albedo effect, which I'll just kind of take you through quickly. So with global warming, we have increasing near surface temperatures, which causes sea ice and over the ocean and snow over the land to melt. So both these substances are highly reflective, and when they melt, they tend to get replaced by surfaces with lower albedo, either the open ocean, or for example, on land, it could be rock or forest. And so these lower albedo surfaces absorb more solar radiation. So either the ground surface or the ocean warm up. And in particular, in the ocean, the mixed layer near the surface will warm. And this, if you like, has kind of a memory of the heat, because in the subsequent winter, when sea ice is trying to refreeze, the ocean is that much warmer, and therefore it makes it more difficult for sea ice to form, or perhaps for snow to lie on land surface. And therefore, again, we have this rise in air temperature, and we have a nice positive feedback loop. And that is one of the principal causes of Arctic amplification. As this diagram shows, there are also other processes involved. So for example, if we have a warmer ocean, we tend to get increased biological activity. And this will emit more aerosols, which are taken up by the lower atmosphere through wave breaking. And they may form cloud condensation nuclei. So these are small particles around which water vapor in the atmosphere can condense. And if that happens enough, then we're obviously going to get an increase in cloud cover. And so more cloud means that traps the outward going long wave radiation. And so we have more radiation or terrestrial radiation in the lower atmosphere, which leads to larger atmospheric energy fluxes into the ocean or to the land surface. And so again, this positive feedback loop continues. There are also remote feedback processes. So for example, changes in ocean currents or atmospheric circulation, and they can either be affected by the increase in temperature or contribute towards it. So Arctic amplification is the change in the mean state, but as Alexander also implied, we have seen changes in the frequency of temperature extremes, and they can actually be far more problematical. So I'm sure I don't need to mention to this particular audience that we saw very high temperatures in the first half of 2020 across much of Siberia. So this figure here shows that case study. So for the first 6 months of 2020, relative to a mean from 1981 to 2010, temperatures were typically about 5 degrees centigrade warmer than average. And indeed, during the 6-month period, we also saw a new record for the observed maximum temperature in the Arctic of 38 degrees centigrade. So as this event was sort of finishing, a new study came out, an attribution study, so a study that was trying to attempt to explain the causes of this particular warming. And this was able to show that the prolonged heat was actually 600 times more likely due to anthropogenic climate change. And the reason they were able to say this was, firstly, that it's the warming took place over such a large area and also for so long. And then they also looked at the average from many tens of climate models. So the effective sample size of their study was very large for this kind of study, and therefore they believe their conclusions are very robust. In terms of the impacts of this particular study, there was the exacerbation of persistent wildfires that we've seen in the Sahara region and others, and also permafrost melting, which was a major contributor to the Norilsk fuel tank spill earlier this year. Okay, quickly talking about something about precipitation. I'll talk about snow cover separately later. So on the left-hand side here, we have annual precipitation trends, again from this reanalysis product. So positive trends are blue, negative are brown. And you can see that across the Arctic region as a whole, we see more blue than brown. And so we see an increase in precipitation rather than a decrease. And again, this is what we might expect because a warmer atmosphere can hold more moisture. But you can see that there are regions, particularly actually in Russia and especially in the Far East of Siberia here, where we have seen quite major decreases in precipitation. So a lot more variability in terms of precipitation than for temperature. On the right-hand side here, we have a trend in these rain on snow events that I mentioned previously with regard to reindeer mortality. You can see at lower latitudes, for example, here across much of Europe, that we've actually seen a decrease in these rain on snow events. And the authors postulate that is because although as temperatures increase, we do get more rain, we also get less snow lying on the ground. However, importantly for the Arctic, you can see that one of the main area where we've seen a significant increase in these rain on snow events is actually in northern Fennoscandia, Kola Peninsula, Karelia area. And these are areas where there is significant reindeer herding, where it's a major part of the economy. And therefore, like the events that I showed earlier, we're likely to see an increasing number of those. Okay, moving on to Arctic sea ice now. So Arctic sea ice decline is really one of the key indicators of climate change anywhere on the planet. I'm sure we've all seen, nasty pictures of starving polar bears and things like that. In particular, we've been focusing on the reduction in Arctic sea ice extent at its minimum value, and that is in September. And so what we see here in this plot is basically a reduction in sea ice extent really since records began, which was with the advent of reasonable satellite data in the late 1970s. And you can see a decline with a minimum in 2012. And in terms of values, I have to apologize, this is an American plot, so it's in square miles, but in 1979, we had 2.7 million square miles of ice. And in 2019, we only had 1.7 million square miles. And so the Arctic is likely to be virtually ice-free if this decline continues by some point during the century, and I'll mention that again later. So that was up to 2019. So there are now automated algorithms for producing daily sea ice extent, and that's what you're looking at here on the left-hand side. So this is a plot I produced this morning, or I shouldn't say produced, I downloaded this morning, and it takes us up to the 14th of November this year. They're produced, as I said, daily at the National Snow and Ice Data Center in Boulder, Colorado. And so we can compare what's happening now with previous years. So as I mentioned on the previous slide, 2012 is where we see the minimum. and that's in the dotted line here. You can see that. And so you can see that 2020 was very low, but not quite the lowest ever. I believe it's something equal second lowest, something like that. But interestingly, if you look what happens after the minimum, you can see that actually this year, the recovery of the sea ice to more average values is taking a lot longer than even in the minimum of 2012. And obviously we can also get maps of where the sea ice is lacking in a particular year. So again, this is 14th of November this year. The median ice edge is shown in this red line here, and the actual ice edge is obviously between the blue and the white. So you can see that this year, where we're particularly missing sea ice is in the northern Barents Sea, and also I guess the Kara Sea as well, and perhaps part of the Chukchi Sea around here. Another parameter of sea ice that we're very much interested in is its volume. Although it's quite easy to measure the extent, we know that a lot of the thicker ice has actually melted now. And so although a lot of the ice that we see now is much thinner, and it's also obviously important to know the overall ice volume. So we can do this by using the extent multiplied by the thickness. And until only about a decade ago, it was very difficult to determine the thickness using satellite data, but we've now improved our techniques for using radar altimeter data, so that we can now use sophisticated algorithms to calculate the thickness of the sea ice, and therefore we can get the volume. And that's what you're seeing in this top panel here. So each of these represents a year. As you can see, we can only get these values as the sea ice increases. Too short a time series to say anything about trends really, but you can see there's a reasonable amount of interannual variability. So for example, there's about 10% more sea ice volume in 2014 as opposed to 2013. Okay, so swiftly moving on to Arctic snow cover. So obviously this forms a very important component of the overall Arctic climate system. It influences the surface energy budget because of its high reflectance. In the winter, it acts as an insulating layer on the ground surface. And in spring, when all the snow melts, it obviously is a major input into the freshwater budget. Therefore, it affects ecosystems in several ways. For example, it can protect plants from the extreme cold in the winter, but if it hangs around later than usual, it will reduce productivity in the summer, and also, obviously, it affects forage, or the ability to forage for wildlife. It can cause natural hazards, it can cause avalanches, and if it melts very rapidly, it can cause flooding events. And this will affect regional socioeconomic activities. Reindeer herding I've already mentioned, but it can affect transport infrastructure. So an avalanche or a flood can destroy a bridge, for example. So very important, both for humankind and also for the natural environment. Okay, so the most obvious parameter measure is snow cover extent, and similar to sea ice, there are now a whole gamut of automated algorithms that combine data from various satellites to produce a daily value of snow cover extent. So what we see in this top figure here is a series of the annual cycle of snow cover extent. Each line represents a year. And so, for example, if we look at 2020 to 2021, which is in red, you can see that perhaps in September we had slightly less than average snow cover, whereas in October you might argue we had slightly more. In terms of longer term trends, we have this bottom pair of figures here. This shows monthly snow cover extent for Arctic land areas in May on the left and June on the right, again, about 50 years or so. And it's divided into North America in black and Eurasia in red. And so what both plots show, the majority of the time, there's a huge amount of interannual variability in both regions. If you look at the longer, or look at the 5-year running means, which is the solid line, you can see certainly there's an overall downward trend. But for example, there are periods like this decade here where we actually see an upward trend in snow cover extent. So quite a lot of decadal scale and interannual scale variability. However, overall, you can see that they both show a decline. And for example, in June, the mean rate suggests that the snow cover extent is decreasing at a rate of 13.6% per decade. Another interesting or useful snow cover parameter is obviously the duration, how long it's lying on the ground. So this top panel shows trends again. You can see that most of the Arctic is red, which means that the trends are negative, so that the amount of snow cover duration is actually declining. You can see there's a lot of variability, but typically about 5 to 6 days per decade. So I've got this pair of figures at the bottom to demonstrate some of the local variability of snow cover duration. This was work done by a former PhD student of mine, Rebecca Vignoles, and she was interested in looking at snow cover duration in the Kabini region of the Kola Peninsula. So for those that know it, this is the Kabini mountain massif here. And so on the left-hand side, this is the mean snow cover duration. And because the mountains are higher, therefore, than the surrounding area, therefore they're colder, and therefore the duration is long, snow cover duration is longer, so they're easy to pick out. But if you look on the right-hand side here, you can see there's trends of both color across the mountain range. I should say the gray areas are basically no data, they're mostly lakes and other water bodies. But if we look at the Kabini Mountains, you can see we have positive trends in red in the high regions, particularly those facing the prevailing winds. And whereas in some of these sheltered valleys here and here, for example, you can see we've actually seen a decline in snow cover duration. So it very much seems to be very much dependent on its relationship with the local orography and the prevailing winds. Okay, now to looking at atmospheric teleconnection or circulation patterns. It's one of my areas of interest. So these describe preferred modes of atmospheric spatial variability. And one of the most important of these patterns for the Arctic, and I think Alexander mentioned it briefly, is the North Atlantic Oscillation, or the NAO. And that accounts for about 30% of the total variance in winter sea level pressure. They're usually defined in pressure or height fields, and the locations of maximum anomalies are called centers of action. So if we look at the NAO here, which is this one in the top left, it actually has two centers of action, but the only one you can see on this figure, because the other one is too far south, is this one here. So this is the Icelandic low. And you can see what happens to this, its location, its magnitude is going to have a big impact across the western part of northern Russia, for example. So these patterns are important because they alter the spatial distribution of wind-induced heat advection and also precipitation-bearing clouds. And obviously both of those will also affect changes in the radiation budget. They're important also because they can be driven primarily by either internal atmospheric dynamics or atmosphere-ocean ice interactions, both of which can be modified by anthropogenic forcing. So looking at changes in the magnitude and frequency of these patterns is a good way of, or another important way of examining Arctic climate change. So one of the things you might want to do is to see how they affect, say, near surface temperature. So that's what this plot on the left here does. This is simply showing the regions where there's a statistically significant relationship between each of the teleconnection patterns and near surface temperature. Positive relationship is red, negative relationship is blue. Now, as this is a sort of a workshop for younger students, I was also going to point out something slightly technical here. One of the issues with this plot as it stands is that it does not account for spatial autocorrelation. There's a lot of false positives in here. And if we do some very basic stats to remove those, we actually get this pattern, or this plot here. And you can see essentially that the amount of red and blue has diminished considerably. And for, using as an example, I want to look at what's called the Western Pacific pattern here. You can see that it has one major center of action on this plot, and that is located over the Northwest Pacific here. But if we look at this figure here, it suggests that what happens to the Western Pacific pattern has a significant impact on, for example, temperatures in the United Kingdom. And it's very difficult to come up with a sort of sensible physical reason why that might be. However, if we remove all the false positives, you can see that any relationship between the Western Pacific pattern and the climate of Western Europe, or at least I should say the temperatures of Western Europe, has disappeared. And indeed, it's only in the Pacific region where you see a significant relationship with temperature. The impact of these teleconnection patterns on part of climates is in northern Fennoscandia. We're looking at the pattern, the one which has the greatest impact on precipitation. So each of these dots, and where we have 50 years of daily precipitation data. And each of these plots is one of the 4 seasons. So we have spring, summer, autumn, winter. And quite clearly from this plot, you can see that different teleconnection patterns are important at different times of year, as well as changing in terms of their overall variability. So for example, in spring, you can see it's the yellow dots that are dominant. So that's a Scandinavian pattern, whereas in summer and winter in this particular area, it's the East Atlantic, Western Russia pattern here in red. In winter, finally, where we have the prevailing winds on the Western Norwegian coast, you can see it's something called the Polar Eurasian pattern, whereas further east, it's actually this North Atlantic Oscillation again, that is the dominant one. Okay, so as I mentioned previously, I'd like to finish off by a quick discussion of how we think the Arctic might change in the future. So these are based on model projections. So climate model projections, and as part of an important component of the IPCC reports are these, what we call CMIP, or coupled model intercomparison projects. And in these, a number of models, typically now about 50 or 60, are forced by various emission scenarios. In other words, how much CO2 and other greenhouse gases we pump into the atmosphere in the future. In this particular, the latest CMIP is CMIP 6, which will be in the IPCC report, which I believe is coming out next year. And their emission scenarios are called SSPs, which are shared socioeconomic pathways. But what you really want to know simply is that there's a range of these. The lowest is where we managed to stabilize the climate by 2060. And then there's the worst case scenario, which is SSP 5, where it's basically business as usual and we don't do anything to reduce our carbon emissions. So if we look at the figure on the left-hand side, this shows time series of anomalies of near surface Arctic temperature. So these are the observations here, essentially in black, and then each of these colored lines represents a different one of these scenarios, or SSPs. So the low emission scenario is shown in green, and you can see in that case, annual mean Arctic temperature is warmed by about 4.7 degrees, as compared to a global average of about 1.7. Whereas in the high emission scenario, shown in purple here, by the end of the 21st century, the corresponding values are 10.4 degrees centigrade for the Arctic and 4.3 degrees centigrade for globally. So it's clear that significant Arctic amplification will continue under all these particular scenarios. Arctic sea ice, we know, is declining. So on the left-hand side here, we have annual data, and right-hand side, you have September data. So this is, again, the minimum value. You can see that the models do a fairly good job at showing the decline in sea ice, although, if anything, they actually slightly over-exaggerate the amount of sea ice they think is in the Arctic. But as I mentioned earlier, if you think that a sea ice decline below 1 million kilometers squared, which is this dashed line here, if you consider that as below that, the Arctic is essentially ice-free, then these models, which again, these are the worst case scenarios, suggest that we're going to have an open ocean by about sort of 2070, 2080. Arctic precipitation next. So if you look at the black line here, which is total precipitation, you can see we have an increase of about 50 to 60% over the 21st century. And that's primarily just because of local warming. We're getting greater regional evaporation. And as I said, the atmosphere is warmer, so it can hold more moisture. What is interesting in this study is the switch from snowfall to rainfall. So you can see snowfall increases slightly and then declines gradually, whereas rainfall increases much more rapidly. And actually at about 2075, according to this particular study, at that point, it will become the main contributor to Arctic precipitation. There will be more rainfall than snowfall in the Arctic by the end of this century. And finally, future projections of Arctic snow cover. This study was done earlier this year, and interestingly, they found that there was a good linear relationship between projected spring snow extent and global air temperature, such that snow extent will continue to decrease by about 8% relative to this 20-year period here per degree centigrade increase in global surface air temperature. So again, if we consider the worst case scenarios, this SSP5, this purple line here, leads to about 55% decline in snow cover in spring and about 60% in autumn. And obviously, as the emission scenarios get stronger, we lose more snow cover. So just to finish up by summarizing the future section then, so it looks like Arctic amplification will continue, whatever we do. Temperatures are likely to increase significantly, and if we don't do very much, they could be up to 10 degrees centigrade in the Arctic, which, as you can imagine, would have a huge impact. Sea ice will continue to decline, and we're probably looking at ice-free summers by the end of the 21st century. Precipitation will also increase markedly, but it'll be rain rather than snow that will become the dominant form. And snow cover extent will continue to decline. We're looking at a reduction likely to be about 50% by the end of this century. And I'll leave it there. Spasiba. Thank you.
Thank you very much, Gareth, for a very interesting presentation. Colleagues, do we have any questions to Gareth? Yes, let me check the chat. Very well, then I have a question. Is there any data on permafrost degradation in the Arctic? Any data that comes from the satellites, or do you use other sources of measurements? What is the scale of permafrost degradation? What is the speed of degradation? Do we have any reliable data?
Okay, so I should begin answering by saying I don't really know all that much about permafrost. That's not my area of expertise at all. I think most of the studies actually have been done in Russia, although clearly it's occurring all over the place. I've certainly seen firsthand what happens in places like in Fairbanks in Alaska, which is also suffering significantly from permafrost decline. I don't, as far as I'm aware, although somebody else who knows more than me could correct me, that I don't think it's monitored regularly by satellite. I think perhaps it's one of those things that you still need people on the ground to take ground measurements and monitor, over long periods of time to really understand what's going on properly. But there may well be other people in this audience who know this subject better than I do.
Спасибо большое. Спасибо.